All right, class. So for this lecture, we're going to be talking about charge transfer at junctions. And really what we're going to be doing is looking at um, the action of charges at the interface in order to derive an equation which will describe how current flows at some of these junctions that we've created. Because this is photoelectrochemistry, we're going to focus on the semiconductor liquid junction, but again, the same concepts are applicable to both semiconductor metal and PN junctions. Okay, so if we're going to draw a chemical equation describing the charge transfer across a semiconductor liquid junction, it would look sort of like this equation here. So we would have an electron in the solid, or equivalently a donor in the solid, and a hole in solution, or an acceptor in solution. All right, so you can imagine our interface. So we have an electron over here and a hole over on this side, right? And we are going to be able to transfer things back and forth, right? So we can transfer it so that there is, say, a hole in the solid and an electron in the solution. So this is the equilibrium. This is the reaction that we're going to be looking at. So we're going to apply this, and we're going to apply a kinetic model, in fact. So we're going to think of this as an actual chemical reaction. We're going to apply the same rate constants and chemical kinetic ideas that we would use for a regular reaction to these systems. And we're going to see if we can obtain that expression for the current voltage behavior. So the simplest model for the electron transfer is going to assume bimolecular kinetics and a simple first order reaction, where the current is going to depend linearly on the concentration of electrons, specifically the surface concentration of electrons, N sub S, which we talked about last time, and on the concentration of acceptor ions, which I'm going to call A. Now, just like in a normal chemical reaction, right, this is like saying if we have A plus, say, B is going to go, or let's think about it this way. A is going to react and turn into B. So the forward rate reaction, the forward rate constant, if we assume a simple first order dependence, is just going to be the rate equal to some rate constant K times the concentration of A. Right? Very easy. Now, we are going to say in this case that it's going to be first order in both our concentration of electrons and our concentration of acceptor ions. You can sort of see by this diagram here what we're looking at. So there's two reactions going on here, really. There's this exchange between the number of electrons, or the concentration of electrons in the bulk and concentration of electrons at the surface. We are going to assume that this is going to be quite fast. And so if we were to sort of look at the kinetics of this, we're going to say that that part doesn't matter. We are most interested in this part right here, in this reaction. So the current is going to depend only on these guys here, which makes sense, right? Because what we're going to do really is we're going to look at the current across the interface. So we care about the current that's going on right here. We don't care so much about what's going on either side here. We only want to know how the electrons are flowing in and out of the semiconductor. So applying our chemical knowledge, the rate of electron transfer is described like this, where we have our rate is going to be equal to a rate constant multiplied by the concentration of electrons at the surface, which we denote as N sub S, and the concentration of acceptors, specifically acceptors at the surface. So this is something that comes up sometimes, for example, in electrochemistry, where unlike in a normal chemical reaction where, you have a flask, right? You got like a liquid in here. And we have like hexagons or something swimming around in here. And reaction rates are going to depend on the concentration of these hexagons because they're all just sort of homogeneous and they're spinning around and they're all running into each other. And this reaction can happen at any point inside this flask, right? This is not so for an electrochemical reaction. An electrochemical reaction, sort of by its nature, we have a solution here, and we have our electrodes. The electrochemical reaction, by virtue of being electrochemical, it happens only at the surface of our electrode here, right? So it doesn't really matter if there's like a super high concentration of our acceptor way down here for some reason. That doesn't affect the reaction rate, because the only reactions that are happening are right over here. So the only reaction, the only concentration that actually matters is the concentration at the surface. So that's why we are being more specific here and saying that it's the surface concentration of our acceptors. But we are going to assume that our system is either well stirred or otherwise well homogenized, such that the concentration of A at the surface is typically going to be the same as the concentration of A in the bulk. But this is going to be a slightly more generalizable expression here by saying it's the concentration of A at the surface. It might be a little weird to include like kind of crossing our symbols here, because this N sub S is equivalent to the concentration of electrons at the surface, but it's going to look a little bit different than what you might expect, where you would see like KET and say like concentration of electrons at the surface, concentration of A at the surface. This is a little bit more familiar to most chemists, but this N sub S is equivalent to this over here, because we're doing work at the intersection of chemistry and physics, so sometimes our symbols get a little bit messed up. All right, so the rate is going to represent a charge flux across the interface. Remember, I mentioned the only current we really care about is right here across this interface, because we assume that once you get over here, it can just move very quickly. And so if it's charge flux across the interface, then that means it's going to have units of per centimeter squared per second, right? We want to know the number of charges that are crossing per unit area per unit time. That's what the charge flux across the interface is. And both of the concentrations, both N sub S and A sub S, are going to be given in units of centimeters cubed or inverse centimeters cubed. Which means necessarily, since we want to make over here, we have centimeters minus 2 seconds minus 1 can be equal to something times centimeters cubed times centimeters inverse cubed. So our dimensional analysis will tell us that centimeter minus 2, second minus 1 is going to be equal to, again, something times centimeter to the minus 6. So in order to make these balance out, the rate constant must have units of quadratic centimeters to the fourth per second. Now, don't try to understand what that means, right? What is a like fourth dimension cubic centimeter, like fourth dimension thing with a centimeter mean, right? Are we like making tesseracts, or what's going on here? I would say it doesn't matter too much. There are papers you can read that can delve a little bit into what the actual meaning of this is. But the simplest thing is to say, well, look at the dimensional analysis. It must be true. So just remember that those are the units that you're going to be using here. Centimeters to the fourth per second for our rate constant. Now, we've only covered the forward rate constant so far. And if you look at our diagram here, yes, we do have a forward reaction where we take an electron out and put it on A, but we also have a reverse reaction where we can take an electron off of A and put it into our semiconductor. All right, and that is going to be equal to, if we look at our system here. So, because what we're doing here is we're taking an A minus and we're giving it to our semiconductor conduction band. All right. So this, if we make a rate constant expression, and we assume, again, bimolecular kinetics, first order in both, we're going to say KET to the minus 1. Remember, this is just the reverse rate constant, not necessarily to the minus 1. And we're going to multiply by the concentration of A minus at the surface. That makes sense. And then we kind of have to multiply by the concentration of states at the surface, right? The states in the conduction band. Those are going to be our acceptors in this case. Well, we have an expression for that, right? We have N sub C, right? The effective density of states for our conduction band. That's exactly what we're looking for. So the rate is going to be equal to KET to the minus 1 times, N sub C times A to the minus S. And then we're going to say, well, this is a constant, right? This is a constant. So let's just include that in here. Let's wrap all these up. And so now we're going to get a rate is going to be equal to a KET minus 1. We can say like prime concentration A minus to the S. So that's what we have over here, where it kind of looks like our equation is now only dependent on the concentration of A minus at the surface. In fact, it does depend on the density of states, but that gets wrapped up into our reverse exchange. We get our reverse rate constant for the exchange. So it gets kind of wrapped up in that. So we don't see it in this equation, but it is there. And that's all this is saying here. Okay, now at equilibrium, we've discussed at length that at equilibrium, there is no net reaction. If we're at equilibrium, it is going just as fast forward as it is going backwards, which means that at equilibrium, these must be equivalent expressions. Now, we're going to rewrite this, except we are also going to now denote this N sub S naught. So this N sub S naught just means that it is the equilibrium surface electron concentration. Because as we do a reaction, right, we are going to change the concentration of both this, and our electron concentration. So it's good to just denote that we're talking about an equilibrium concentration here. Technically, this is true for both of these as well, but again, we're going to kind of assume that we're not changing their concentrations too much. Okay, so we're going to set these two equal to each other. And we are going to say, okay, well, the net rate of reaction is going to be given by the rate of change of electron concentration at the surface. So net reaction rate is the derivative of the number of electrons at the surface with respect to time, which makes sense, right? If we imagine a plot of N at the surface versus time, if that's not changing, our reaction rate should be 0, right? And thus, the rate of reaction is 0. If it changes really fast, let's say it decreases really fast, that's a very quick rate of reaction, right? Because we have now taken away a whole lot of electrons very, very quickly. Perhaps it now increases very slowly. So now we have a slow rate of reaction to increase the number of electrons at our surface. So the derivative of this graph would give you the reaction rate at any given time. So I'll get rid of this. We also say it's the negative derivative. And that's because if electrons are coming out of our semiconductor, which would mean that the concentration of electrons at the surface is changing or is decreasing, that we're going to call forward. So that we want that to be positive. So if, like in that example before, we decrease the concentration of electrons very rapidly, we're going to get a negative derivative, but that is actually a forward rate. And so we're just going to pop a minus sign on it right here to say, oh, actually, that'll give us a positive net reaction rate now. And because this is a pretty simple reaction here, the rate is going to be the forward rate minus the reverse rate, right? So we are going to take our new expression for the reaction rate. We are going to set it equal to our forward reaction rate minus our reverse reaction rate. And that's our expression. But we have seen this expression before. And if we assume that this doesn't change very much with time, which it typically doesn't, we can use our equilibrium expression. And we can set that equal to the forward reaction rate constant times the concentration of A at the surface multiplied by the equilibrium concentration of electrons. So we're going to do that. We're going to substitute that in. And that will give us this expression here where we have KET and KET. We have A and A. So we're going to combine all of that down here. So now we have the forward reaction rate constant multiplied by the concentration of acceptors at the surface multiplied by the difference between the current surface concentration of electrons and the equilibrium surface concentration of electrons. Just to double check, let's do a quick check on ourselves to make sure that we are actually looking at the right thing. So at equilibrium, we should expect that the rate of reaction is 0. So let's plug that in. So at equilibrium, the concentration of electrons at the surface is the same as the equilibrium concentration of electrons at the surface. So this becomes n sub s naught minus n sub s naught is going to give us 0. Multiply that by 0 is going to turn this whole thing into a 0, meaning that we have no net reaction rate. So this seems to hold up under equilibrium. All right, neat. So what happens if we if we increase the concentration of electrons? Well, if we are increasing the concentration of electrons, this is going to decrease, right? Because if we look at our expression here, it's going to depend linearly on the concentration of electrons, but we are going to reverse it. So if n sub s increases linearly, then the rate of reaction is going to decrease linearly, and vice versa. If we decrease the reaction rate constant, then the rate will now increase. That shows that the rate has increased. And thus the semiconductors are going to flow, right? Hold on, let me double check myself. Yeah, so if we increase n, we get that this expression here, we get that this expression here is going to get larger, right? Because we're going to get a positive number. Yeah, because we're going to get a positive number here, which means that the reaction rate is going to go down, right? No. Okay, no, let's think about it this way. We have increased the concentration of electrons at our surface, right? So we start here, we have some n, and there's a rate at which it's going forward and backwards. If we increase the number of electrons over here, we are going to increase the forward reaction. And so electrons are going to flow into the solution. If we decrease the concentration of electrons, we are going to increase the reverse reaction, which is going to mean that electrons flow from the solution into our semiconductor. Yes, that makes considerably more sense. Okay. All right. So now we can make an equation that describes the interfacial charge transfer. because current is just an electron transfer rate multiplied by the fundamental charge, right? So we actually get this into coulombs, and the area of the electrode. Because remember, before we have been saying that this is an electron flux, which is a number of electrons passing through this interface per unit area per second. So we are going to say that the current here, denoted by I, is going to be equal to the fundamental charge with a negative, because we're working with electrons here, multiplied by the electrode area, multiplied by the rate of the reaction, which again has that minus sign. And then we are going to assume that our concentration of A is constant, which we can because we're assuming that the number of electrons at the surface is much, much smaller than the concentration, which we have shown in problem sets and in lectures is generally the case. And thus, we can write this out a little bit more. So we are going to say expand this expression up here to its larger form. So we now have the fundamental, we have the reaction rate constant, KET. We have the concentration of A at the surface, and then we have our surface electron concentrations. Then we're going to combine all of this stuff, which is all just constants, and we're going to make a new constant. I'm going to call it C, because I don't want to write all this all the time. So we now have a new constant and a much simpler expression that the current is going to be equal to the a minus C, which is again equivalent to all of this stuff, multiplied by the difference between the current surface electron concentration and the equilibrium surface electron concentration. All right. Now what we're going to do is we are going to pull the n sub s naught out of this expression. Really, the reason that we're doing this is because we want to divide n sub s by n sub s naught. And this will be important in a minute. So for now, let's just say that this is a little mathematic trick that we're going to do. It'll end up looking like this. All right, now we're going to take this expression and we're going to put it aside because we are going to come back to it. But for now, set it aside. Now, in one of our previous lectures, we looked at an expression that got the surface electron concentration for us. Remember, it had that Boltzmann relationship. So the surface electron concentration is going to be equal to the bulk electron concentration multiplied by an exponential of negative Q VBI. Remember what we saw, if there was larger VBI, we would get fewer electrons at the surface, divided by KT, which is just room energy. So what's interesting about this expression here is we now have a voltage to play with. And kind of at the beginning, I alluded to the fact that we wanted to see the current voltage behavior of these systems. And we notice here that we have a way to relate the current to N sub S. And we also have a way to relate the voltage to N sub S. And we can also see that if we apply a voltage to our system, we can modulate the voltage that we would feel for this expression here. Right? I say that we modulate VBI. We don't really modulate VBI. We are modulating the potential of the system, and thus we are modulating this term here in the expression, which is going to cause a difference in the surface electron concentration. So we're going to start with neutral. This is where we just have our VBI. We know how to find that. We know what it means. But then if we apply a positive potential, what happens is the band bending increases here. We're going to pull them further down. So the voltage that we measure here is now going to be equal to VBI plus our applied voltage. Similarly, if we apply a negative voltage, we're going to bump our bands up a little bit. And so now the voltage that we measure is going to be equal to the built-in voltage minus our applied potential, right? So it seems as though we can add the value of our voltage, whether that value be positive or negative, to VBI and get the right expression for how these the band bending diagrams change. So that's what we're going to do. We're just going to replace the QVBI with QVBI plus V, this V being a V applied. All right, cool. Now, we are going to bring back our old expression. Excellent. So we see that N sub S divided by the equilibrium N sub S is part of this expression. Let's evaluate that. So I'm going to take N sub S divided by N sub S naught. Those are both going to be equal to N sub B times exponential of all sorts of stuff. So the N sub B's cancel out. And the exponentials you could expand to say that this is really exponential of QV minus QVBI or KT minus exponential, or actually really multiplied. Yeah, multiplied by exponential of minus QV, right? Because we need to distribute this minus sign, minus QV over KT. Both of those are going to be over exponential, QVBI KT. So these two expressions cancel out, but this one is left alone. And that, oops, that is how we get this expression here, that the ratio between the surface electron concentration at non-equilibrium to at equilibrium is equal to the exponential of negative Q times the applied voltage V times, or divided by KT, which is just thermal energy. Get rid of all of this. All right, now if we plug this into our equation from before, we get that still big constant minus C multiplied by the equilibrium electron concentration at the surface, now multiplied by exponential of minus Q times V divided by KT minus 1. So if you look, now we have an expression relating current to voltage. So now we should be able to measure we should be able to apply a voltage to our device, which is pretty easy, measure the current, which is also pretty easy, and learn, we should be able to, one, predict what should happen, and we can learn a little bit about the semiconductors this way. So what happens if we apply voltage? Let's start by applying a positive voltage. All right. So if we plug it into our expression here, which remember is I is equal to negative C, draw that better, equal to negative C N sub S naught multiplied by the exponential minus QV KT minus 1. Which, by the way, this is a super important expression. We'll get to a better form of it later, but this is going to be very important to remember. Okay, so if we make V positive, we are going to get an exponential of a negative, right? Because everything else in this is positive, K is positive, T is positive, and Q is going to be a positive number. Then we have that minus sign in it, so that whole thing just becomes negative. Right, and recall that E of 0 is equal to 1, so E of anything less than 0 is going to be less than 1. So e to the minus something, which is what we have, is going to be less than 1, which means that our expression here is going to be equal to negative c and s divided by something that's less than 1 minus 1. So we know two things about this. One is that it is going to be that this side is going to be negative. It has to be. And it's also going to be at most 1, right? Because really when I say that this is less than 1, I should say that it is less than 1 and greater than 0, right? Because we can't quite get to 0 with these expressions. So at most, this is going to be minus 1. And we have a minus out here. So this whole expression is going to be positive. And it is going to be at most, right? If our largest possible number is 1, this is going to be at most C n sub s naught. That is the largest it can possibly be. But it will probably be smaller than that. And not only that, because we are restricting our values here, and we have that minus 1 in there, there is going to be a pretty small dependence, right? Because if you imagine, this is going to be in 1 over e to the something. So this already isn't going to change a whole lot. But then when you add that minus 1 in there, you're setting sort of a bound here with that minus 1. So if this continues to get smaller and smaller and smaller, that just means that the expression here, that the current is going to change less and less and less. So the larger V is, the less the current changes. But it will be positive. All right. The next thing is to imagine what happens if the voltage we apply, is negative. All right, so let's do the same thing we did again. Well, we'll get that QVBI. So this is now going to be the exponential of a negative times a negative, which is going to be equal to exponential of a positive. All right. Now the exponential of a positive is going to be at least like 2.7. Really, it's more than 1 because the lowest it can be is 0, but like I'm going to assume we start with 1. I probably shouldn't. This is, yeah, let's do it that way. It's going to be greater than 1. And it's usually much, much greater than 1, right? Plus, if you consider, so we have Q times V, right? Negative Q times V. I'm just going to get rid of the minuses because they're going to kind of cancel out. So what's the typical applied voltage for a semiconductor? Generally, we go up to a volt. So let's say half a volt, right? 500 millivolts. So 500 milli-electron volts is like a typical number that we might apply to a semiconductor. And we divide that, by KT, which, if you don't remember, is about 25 milli-electron volts. So this is like 20 times larger. So this is going to be like approximately e to the 20. So these can be quite large. These numbers can be very, very big. Right, and instead of being bounded by their upper bound, we are now only bounded by a lower bound. And so in this case, the current is going to be at least, right? It's going to be, it could be 0, right? So we'll get to that actually. If it's positive, it's going to be at least 1. And it's going to continuously increase. Although it's going to increase in the negative direction here because of that minus sign. Now, if the applied voltage is 0, we get QV, KT is equal to 0, which means e to the 0 is equal to 1, which means we get I is equal to 0. So at 0 applied voltage, we get 0 current. So what does this look like physically? All right, so we looked into the math of how all this might work, but does it actually work like conceptually for the physics? Yeah, it does. So what we're doing here, if we apply a negative voltage, so V is less than 0. Remember, we are pushing our bands up a little bit. And so this reaction remains nice and fast. And then we are increasing the concentration of electrons at the surface, which means we are increasing this rate. It is going to be faster and faster and faster for us to send electrons out of our semiconductor and into the surface. Also note right here, our Fermi level and our electrochemical potential for our acceptor are no longer equivalent because we are no longer at equilibrium. So the Fermi levels are only equal to one another at equilibrium. It is possible for them to be separated. But yeah, so the takeaway here is that it does make sense. The bands bend a little bit less. And so we are increasing the concentration of electrons at the surface, which means that we are increasing the forward reaction rate. So we're getting more of our acceptors to be reduced. We're adding more electrons. Where if we increase, we have a positive voltage that pulls our bands down. Again, you can sort of see with the Fermi level there. And we get the equilibrium here is going to be a little bit slower. We're going to decrease the concentration of electrons at the surface at equilibrium, which means that we are going to speed up the reverse reaction. We are going to speed up electrons getting added to the semiconductor. So that's what's going to be happening there. So that makes sense. That makes sense physically and with our math. We can simplify a little bit more. So we're going to combine some constants again. We're going to say that C multiplied by N sub S naught is equal to I sub 0, or I naught, which we're going to call the exchange current. So that's the current which is flowing at equilibrium. Now it's flowing in both directions because it's a kind of a confusing thing to say because, you know, like when we say like, well, there's no net reaction rate, but there are reactions going on. It's kind of like saying, well, okay, if there are reactions going on, how quickly are they happening? Right? Because we know that at the surface, there is some rate at which we are turning our A into A minus, but we don't know what that rate is necessarily. But that's what I naught is. That is our exchange current density. That tells you how fast this is happening at equilibrium. So even though you don't measure an actual rate of anything happening because the net reaction is 0, there are two things happening, right? Where we have an electron going to a hole, and they are happening at a rate, and that rate is I naught. It's just that they're happening at the same rate in opposite directions. So if you take the whole system, there's a net current of 0. So hopefully that makes sense. And that brings us to this expression, the ideal diode equation. The current is equal to negative exchange current multiplied by exponential of negative QV over KT minus 1. This is the equation for diodes. It's super duper important. You should write it down. You should memorize it. It is going to come in real handy, and we're going to modify it a little bit. But this is its ideal form. Now, we discussed that in one direction, if we apply the voltage, we get small current, and it's got an upper bound to it, which is the exchange current density. On the other side, we have a large current. So what we have here is one side of the voltage spectrum where current flows freely, and we can push as much current through it as we want effectively. But the other way, we can apply a pretty high voltage and get almost no current, right? Because remember, we're getting to that upper bound of the exchange current density. So that's called rectification. And that is characteristic of a diode. That's what a diode does, is it stops current from going in one direction and allows current to go in the other. So we can plot this ideal diode equation with, say, an N-type semiconductor. So in the positive region where we have a positive voltage, we have the rectifying region. So this is where the current is attenuated, or it doesn't matter how high we apply the voltage, it's going to be at most the exchange current density. So the current approaches I naught. And then, of course, at V is equal to 0, we have the current is equal to 0. And then at a negative applied bias, we are going to have a really high, excuse me, we're going to have a very high current because we have an exponential dependence now of current on voltage. Now this is for N-types. We've been doing this whole thing deriving for an N-type semiconductor. P-type semiconductors work very similarly. You can rederive it if you want. I don't recommend it, but you can. The expression changes to look like this. We just kind of take out those negatives, just flip the signs because everything is just happening in reverse. And in that case, the graph just gets flipped. So now if you apply a negative voltage, you get almost no current, and it's going to be negative current. And if you apply a positive voltage, you get a very high current, and it's going to be a positive current. All right. So we call these diagrams IV curves. And we use these to learn about junctions. So I naught is actually probably the most important parameter for right now. So I naught is our exchange current density. And remember, it contains our electron transfer rate constant. So if you know I naught, you can figure out the kinetics of electron transfer across your interface. And also, because it contains this, you can just sort of use your chemical intuition to understand a few things. So if your charge transfer is really, really easy, let's say it's very easy to pull those electrons off your semiconductor, your electron transfer rate constant is probably really high, which means your exchange current is probably very high. You can also get this to happen if, say, your built-in voltage is really low, because then if VBI is low, then the difference between the concentration of electrons in the bulk and at the surface is very low, which means that that ratio is going to be rather close to 1. And so you get like larger and larger and larger I naught. Right? If we increase the concentration, remember it's equal to I naught. I naught is going to be equal to negative C. Oops, not negative, just C NSO. So if we decrease the VBI, we're going to increase that because of the Boltzmann relationship. Remember, larger band bending equals less electrons at the surface. So that can also increase our exchange trend or exchange coefficient and our exchange current. Generally, we prefer devices that are good rectifiers. So our good diodes like have this small KEC down here. If you have a whole lot of what's called dark current or a lot of current, a large exchange current density or current, you might be your semiconductor might be called leaky because it sort of is leaking charge across its interface, even though it's supposed to be stopping it. It's letting a fair amount of it go. It can cause decreases in efficiency and things like that. But that is all we have for today. So I will see you in the next lecture.